Bone formation, also known as osteogenesis or ossification, is the process by which bone tissue replaces embryonic connective tissue to form the skeleton. From childhood to early adulthood, ossification lengthens and thickens bones. In addition, the process of ossification is used throughout life for bone remodeling. There are two methods of prenatal bone formation: the intramembranous ossification and endochondral ossification. Let us begin with the intramembranous ossification. During intramembranous ossification, bone is generated on or within fibrous connective tissue membranes. As the process begins, mesenchymal cells differentiate into osteoblasts in regions called ossification centers. The osteoblasts secrete osteoid or uncalcified bone matrix. Over a few days, osteoblasts become osteocytes, and calcium and other mineral salts are laid down, hardening the matrix. The bone matrix develops thin columns of bone called trabeculae, which fuse to form spongy bones. Blood and lymphatic vessels grow into the surface of newly formed bone and develop red bone marrow. Outside of the bone, a dense layer of connective tissue called the perosteum forms. Most outer layers of spongy bone are eventually replaced by compact bone, but the centers remain spongy. Intramembranous ossification also occurs with skull bones in childhood. At birth, skull bones are separated by fontanelles, or soft spots, and also sutures, immovable joints made of fibrous tissue. Fontanelles in the fetal skull allow for easier passage through the birth canal and rapid brain development up until adolescence. The fontanelles slowly ossify into sutures, providing the brain with greater protection. Now let's take a look at endochondral ossification. Endochondral ossification, or the replacement of cartilage by bone, occurs in most bones of the skeleton. The process begins with embryonic mesenchyme condensing, forming a cartilage model, which is the shape of future bone. The model grows within the fetus. Lengthwise, known as the interstitial growth, or in width, known as appositional growth. A nutrient artery penetrates the perichondrium, increasing nutrient availability to the cells. Osteogenic cells are stimulated to differentiate into osteoblasts. These cell stimulus secrete matrix beneath the perichondrium that forms the thin cell of compact bone known as the bone collar, or the thin shell known as a bone collar. As the perichondrium begins to form bone, it is now called perosteum. The bone collar reduces diffusion to the cartilage inside the model, depriving it of nutrients. Capillaries grow into the disintegrating cartilage, displaying or delivering osteoblasts. The new growth forms the primary ossification center, an area where bone tissue will replace most of the cartilage. Osteoblasts deposit bone matrix, building spongy bone trabeculae. The growing model is gradually remodeled, but the cavity is filled with capillaries and red bone marrow. Ossification proceeds, forming the main portion of the bone known as the diaphysis or diaphysis. Around the time of birth, blood vessels enter the epiphysis, the ends of bone, forming a secondary ossification center. Secondary ossification differs in that no medullary cavity forms and ossification proceeds outward. As a result, the interior of epiphysis remains spongy. Secondary ossification leaves a thin layer of hyaline cartilage covering epiphysis or epiphysis. This is known as the articular cartilage, and it reduces friction and shock in the bone joints. The change to epiphysis also forms the epiphyseal plate, which is a layer of hyaline cartilage that enables the diaphysis to grow in length.